Welcome back to the classroom. My name is Miss Nong. Today we're going to be talking about drawing Lewis dot diagrams. So what we're going to firstly talk about is a recap on what covalent compounds are. And then we're going to talk about how to draw Lewis dot diagrams, what can it demonstrate to us for covalent bonds. Hopefully by the end of this lesson you'll know what these diagrams do and how to draw them as well. Firstly, what we said is that covalent compounds is formed when two or more nonmetals combine and share their valence electrons. The idea is when we're forming covalent bonds, following the octet rule, we ensure that the valence shell, so the most outer shell of all the elements, are completely filled, and then therefore we have a stable compound. This actually goes back to the idea when we talked about the electron shells with the Niels Bohr's atom. So you might remember that in the dead center you have protons and neutrons, and then you have electron shells. Depending on which shell you're in, there is a fixed number of electrons that can coexist. Now, what we do know is if we're in the first shell, or if you're reading off your periodic table, the first row, you have a maximum of 2 electrons in that shell. If we're counting through the second row, second shell, you have a maximum of 8 electrons. If we, at the third shell, we have a maximum of 8 electrons as well. If we actually look at the electron configuration of oxygen, it is 2 and 6. Okay, so what that means for oxygen here, so we can tell that it's in row 2 and that it needs an additional 2 electrons for a full valence shell. What that can also mean is it's going to be reactive. It's going to try and react with something to make itself form into a stable compound. So it's going to be reactive in order to become a stable compound. At least that's what it's hoping to do. If we actually have a look at some of the most reactive chemicals on the periodic table, group 1 and group 7 or 17 are the most reactive elements you'll find. The reason for group 1 is because it wants to lose only one more electron to obtain a full valence shell. For group 7, it wants to gain 1 electron for full valence shell. The reason why group 18 or group 8 are so stable is because it's a full valence shell. Hence why they're called noble gases, hence why it's also known as inert gases. To represent the number of valence electrons for a particular element, we can use a thing called Lewis dot diagrams. It's actually quite useful when it comes to covalent compounds because it actually tells us where the bonds are being formed, how many bonds are there in total, are there any repetitions, so that's quite useful there. A couple of things I would just like you to note is that when drawing Lewis dot diagrams, all you need is the symbol of the element you want to draw and the number of valence electrons. To work that out, simply look at which group number it's in and it'll be pretty easy. So let's check that out. So the general rule of thumb is in terms of valence electrons. If it's in group 1, it will have 1 valence electron. If it's in group 2, there's going to be 2 valence electrons. Group 3, this in the case is group 13, 14, 15, so on and so on. This would have 3 valence electrons. Don't get this confused with the charge number. So charge number and number of valence electrons are different. So don't confuse that. That's 4, that's 5, that's 6, that's 7, and this is 8. We said that for helium here, it's a maximum of 2 because it's in the first row. Okay. If I want to draw, let's say, the Lewis dot diagram of silicon, it's in group number 4, so I know that it has 4 valence electrons. So I'm going to do 1 dot here, 1 dot here, 1 dot here, 1 dot here. Generally, you want to even them out first before you pair anything up. So there's that. If I do chloride or chlorine, it's in group 7. So it has 7 valence electrons. So 1, 2, 3, 4. So I've put 4 in all directions. Now I'm going to pair them up. That. Okay. If I look at neon, it has 8. So 1, 2, 3, 4, 5, 6, 7, 8. If I look at sodium, it's just going to be 1 because it's in group 1. Hydrogen is going to be 1. Lithium is going to be 1. Now, if you actually have a look here, like we said before, everything wants to have the same configuration. So all the elements want the same number of valence electrons as group 8. So here we see with chlorine, it wants an additional of 1 electron to get there. For sodium, it's actually a lot easier for it to lose that 1 electron and then have the same configuration as neon here. If chlorine does have an additional electron, then it will make itself into a chlorine ion. And then in that case, we can just simply show it like so. This negative representing how we have 1 additional electron. So that's how you draw a simple dot diagram for elements. So Lewis dots, if you want to use it, you are trying to represent the number of valence electrons for any atom, compound, or molecule. If you want to be fancy and you want to show the type of bond or the number of bonds formed, we call it a structural formula. So when oxygen bonds with oxygen, there are 2 bonds. We call this a double bond. Okay. The reason why it is a double bond, you can actually see here with oxygen. Now for oxygen to be stable, it needs 8 valence electrons. Here we have 1, 2, 3, 4, 5, 6. Oxygen naturally has 6 valence electrons. By forming 1 bond here, or let me just count up. So 1, 2, 3, 4, 5, 6. If it forms a bond with another oxygen, it's, remember, sharing the electrons. So this is 7 valence electrons with oxygen here. There's still 1 more required to get 8, so it forms this one here, and then we get the 8 valence electrons. The same effect works for the other oxygen atom on the other side as well. If we have a look at the number of bonds, let's have a look here. So firstly, let's look at this molecule. We have sulfur trioxide. So the formula is SO3. S representing the 1 sulfur, O3 representing the 3 oxygens here. So what we see is we have a double bond here, we have a double bond here, and we have a double bond here. So we have 3 double bonds. Here we actually have what we call a triple bond between the carbons, and we have a single bond between the carbon and hydrogen. So how do we know that we get doubles, singles, or triples? This is where the Lewis dot diagram comes in handy. Okay, let's look at some examples here. So we have hydrogen sulfide. We know that hydrogen has a valence electron of 1, so 1 valence electron. Fluorine has 7 valence electrons. So for hydrogen to be completely stable, it needs 2. Fluorine needs 8. So let's just draw this one here. fluorine on this side goes 1, 2, 3, 4, 5, 6, 7. That 7 forms a bond with this one here, and that becomes 8 for our fluorine, and that becomes 2 valence electrons for our hydrogen. You can see there's only one bond formed, so it is a single bond. Okay, here we have carbon. So carbon has 1, 2, 3, 4 valence electrons. It needs 8 to have a full outer shell, which means that carbon is a special case. It can form up to 4 bonds. Now, in the real world, we never see a quadruple bond. We only see triple bonds as the maximum, so keep that in mind. We have our hydrogen. So one hydrogen is going to contribute 1 electron. Right now we have 5 in total for our carbon. 6, 7, and then 8. You can see here there's not, the reason why we need 4 hydrogens is because whilst the hydrogen itself only needs 1 to have a full outer shell, the carbon still needs another 3 contributing. So that's what we have here. Number 3 we have is phosphorus, so that's 5 valence electrons. And then chlorine, it has 7. So there's that, running out of space, but this is how you draw it. If I want to draw the sort of structural diagram, this is what it will look like here. And this is what it'll look like for this one here. Okay, so that's what we got. So all of these are single bonds. Under what scenario could we get double bonds or triple bonds? Okay, let's have a look. Now let's use the case of nitrogen here. Nitrogen has 5 valence electrons. Let's have a look. So nitrogen, we have 1, 2, 3, 4, 5. So if this bonds over to this one here, that's 6. But we still need 8 in total. That's the ideal outcome that we want. So let's say this electron here forms another bond with this one here. So we have 7. So now we have a double bond. That's still not enough to have 8 valence electrons. So, okay, let's be a bit more generous. Let's give this other electron and make it bond with this electron here. Okay, now this electron becomes 8 for the nitrogen on this side, and because it's being shared, so nitrogen will also have 8 on this side as well. So in this case, we actually have 1, 2, 3, 1, 2, 1, 2, 3. We actually have a triple bond. Okay, so that's our triple bond there. If you actually did the one for oxygen, you'll work out there is a double bond. Chlorine is just a single bond. So that's kind of how you can work out the number of valence electrons for an element, and then also work out the number of bonds and where the bonds go when you're drawing for covalent compounds. So hopefully that helps. Another thing you might want to know is writing the chemical formula. So we have 2 nitrogens, and so we just write N2, and that's it. So hopefully that was helpful in understanding how to draw out Lewis dot diagrams. If not, if there's something of concern that you still didn't quite get, please rewatch the video, and always thank you for watching.